this one. So I have a lot of different practice problem sets and stuff like that. So you have more than enough, practice problems to work. I'll try to get the answers to all of these up here. But as always, there is a formal assessment or review for the assessment. Come on. Computers acting silly. That review starts on page 18 and 19. So if we take a look, we should know the dilution formula. Most of the time with the dilution formula, you're looking for the size of the cap. That means you're looking for volume 1, right? The size of the cap. Should know the boiling point elevation, freezing point depression, vapor pressure lowering, and the osmotic pressure. That's that pi equals molarity times RT. Make sure I don't want to say that wrong. I forget the I. The index. The hardest part for this one is remember that it is the moles of the solvent. It's the mole fraction of the solvent. But with that, you also need to have, so it's moles of solvent. You need the moles of the solute plus the moles of the solvent on the bottom. What do we have to do to the moles of solute here? We have to multiply it by I. Because the bottom is supposed to be the total moles of particles. And if the solute dissociates, then it's going to have a number of particles per mole of I. So that's a big one. That's one that mostly is forgotten. Then people are like, oh, boom. Vocabulary, miscible, unmiscible, unsaturated, supersaturated, colloid, suspension. Suspension, the particles settle. This is a mixture where the particles settle. We talked about this stuff more in the summer packet, but this would be like chocolate milk. If you let Hershey's chocolate milk set, what do you come back to? If you let it sit for 10 minutes, you come back to a glass where the chocolate is down here in the bottom and the rest is the milk. So that's what happens during a suspension. The particles settle down to the bottom. A colloid is like toothpaste. Basically, this is just because of the size of the particles. The size of the particles in the suspension are pulled down by gravity eventually. The particles in a colloid are not. Just like the particles in a solution would not be. The Tyndall effect. The Tyndall effect is the basically the scattering of light. Sure. Been a while. I'm gonna make sure that that I'm right on that. The Tyndall effect, yeah, it's a light scattering of a particulate matter dispersed in a solution. So normally light travels through air and we cannot see any difference. What if there was a cloud of dust in the air? Have you ever seen that? Sunlight coming through a window and you're like, man, this place is dusty, as you see kind of like all the particles shimmering and giving off that light, right? You could also do this if you've ever seen a movie where they're like, see how you can't see that laser until it hits my hand? If I go get a glass of water real quick, let's take a look and see if we can get it. So what's the movie where they're bad guys? brought the smoke down and then the lasers, then I can see all the lasers.
That's been a lot.
No, just one. I don't think so.
Probably impossible.
Probably that's impossible.
Maybe.
Is it in the Matrix?
No, Matrix where Keanu Reeves did the whole
Oh. So even here, it's hard to see that laser light through there. Let me add two things to it real quick. In the water. So our water is chlorinated. So here I've got a solution of a silver nitrate. If you recall from last semester, any nitrates dissolve. They are completely soluble. Silver will pair up with chlorine from the water. And now let's see. Come on, man. Oh, dang it. I'm a foolish man. You know what I put in here? I put distilled water. Give me 1 second. I got to get tap water. What's that? How much more do you put in tap water? Oh, let's see. First off, this is a school water. So do you think this is school tap water? That just gives us an idea of how pure our distilled water is. That was pretty cool. So take a look. Is there a little bit more that you can see of the laser in there? Yeah, right? We can actually see a little bit more of that laser in there. Hopefully. And watch this. We put that silver in there. It's going to react with the chlorine from the tap water. That's going to increase the Tyndall effect. Take a look there. I'm in my hand. Yeah, right? So you can see now that laser is scattering off of that precipitate that's forming in there. And I'm just wondering, like, you can't unfortunately make it darker, maybe? Dimmer? Yeah. So you can see that we can definitely see that laser all the way across there. That's the Tyndall effect. Now, the cool thing is that's what we're going to use with the Spec 20s I was talking about for the laboratory. So it shines light through different wavelengths through the actual solution that you're looking at. Now, remember what we said, that if, for example, my shirt is blue, in reality, my shirt absorbs every color or a lot of the colors except for blue, right? Blue is reflected. That's why I see blue on my shirt, or red, right? So different wavelengths of light will actually be better for different chemicals. What was the color of the chemical that you guys made last week?
Red.
Reddish, right? The cobalt 2 nitrate. So we're expecting that to reflect a lot of red. So we would not assume that a wavelength in the red spectrum will be good for that, because we want it to actually absorb the wavelength of light that we're shining through it. So that's the first day of experiment. We are going to try to figure out which wavelength of light is best. So let's take a look here, get that off there for you. Formulas for molarity, molality, mole fraction, and mass percent. As I said, those were graded. You can take a look at those. If you did poorly on those, please check, see if you understand what you did wrong. Apply the principle of likes dissolve likes. We did the hot sauce and chicken wing day. Effects of temperature on and pressure on solubility. I can't remember the boy's name, but we saw that the solubility of gases for him was not too good. I remember temperature as well. That's that whole solubility worksheet that you guys did. Compare dissolution of ionic versus molecular solids. That's what the whole I factor is. Interpret and apply solubility curve data. We'll do that down here. The lab information, making solutions, and the Spec 20. So those are the basic things. Here are some practice questions. For the following, identify whether the substance will dissolve in polar or non-polar solvent. How about this sodium nitrate? Polar, right? Because this is ionic, it will dissolve in polar. How about this carbon tetrachloride? Right, we have 4 bonds, it's tetrahedral. So it is non-polar, so it will need to be in non-polar. Basically go through the rest of that. Which compound solubility is most affected by temperature change? Here and here, which one's affected most by temperature change? A, as the temperature increases, A's solubility really goes up. Which of the 4 compounds could be a gas? There's not 4, there's only 3. C. Why is it C? Because as temperature goes up, solubility goes down. If you were at X, which ones would be unsaturated? If you mark the point X.
A and B.
A and B would be unsaturated. C would be supersaturated. That's the hard one, right? I don't think you guys are to the point when you can just look at that and think. Actually put your pencil on the point or your finger on the point and say, okay, if I have this much of the stuff, I am over the amount of C I should have, so that should be supersaturated. I can still add more B and more A, so they must be unsaturated. I think it takes that physical pressure on there and the thinking about it before you get to the point when you can do that very easily. Then it's just a lot of math, which the majority of this has always been. So I'll let you take a look through those. Now I just want us to just think about this just conceptually, just what we understand about light and mixtures themselves. So it says using the absorption plot, and this is what you're actually going to make this week. You're going to take the concentration is the independent variable. The absorbance of light is dependent on the concentration. As the concentration goes up, more light is absorbed. Does that make sense? If we have more particles in there, they're going to absorb more of the light going through. So using the absorption plot shown in figure 2, if you ran an unknown sample and recorded the absorbance of 0.390, what would you approximate the concentration to be? So you will be doing some unknowns, right? So the absorbance is 0.390. So that's the reading that you get. Here's 0.2, here's 0.3, right about here's 0.390. So we will come over to here, and then we will go down, right? So by making this graph, we can then make this line. The line has to go through the origin because with zero particles there, you're going to have zero absorbance. With 0 particles there, you're going to have 0 absorbance, right? So yeah, this could be a little bit straighter, I guess. So which one matches up best with this? 0.006. That's too low. That's too low. We're not off the scale. So it must be 0.0067. And you will have 3 unknowns that you will do this to. So the first thing you will do on Thursday is find the best light wavelength to use. Friday, you will plot out 1, 2, 3, 4, 5 different concentrations, I believe. And then after you make this line, you will do the unknowns. You don't need to make this graph before you do the unknowns. All you need to do is get your 5 and then do your 3 unknowns. And then you'll be able to take that information home plot the graph, and then do the unknowns. Scattered plot with 0.00 being one of your points, and then draw best fit. I believe that's the best way to do it. Yep. I think there's actually a video in the a video and an actual spreadsheet to get you started in the link for the assignment. Questions there? This is known as Beer's law of absorbance. Now, today I'm going to give you just a general look at the machine that you're using. I don't know what the easiest way to do this is, so we're just going to do it. Yeah, you get the real life version, right? Yeah, that's fine. So this is the machine. This is how you turn it on. I don't know if any of you have ever had a, let's see here. Can I get this right? Had something that turns on like this, but you turn this knob until it clicks. That's the gist of it. I almost think I want the other camera. Let's try this. A lot going on here. That won't work. That might be as good as we can get it, guys. Just gotta make sure I don't throw this computer off into the floor. I'm gonna move everything over a little bit more. All right. Can you see the 525? Olivia? I need to boost
Not
this.
really.
Not
I'm trying
really.
to-
Let's see if I can boost this computer up a little bit to my height.
You're still sharing, so I can't like pin
Oh,
you.
what? It's a real little one. I need to stop sharing. I thought it stopped shared as soon as I pulled that out of there. How's that? Better?
Yeah, that's better.
Okay, cool. So this is the machine. There is a light bulb right here. Yeah, sorry. You can watch it up there too. Up to you. There's a light bulb right here. This is where you put your little sample. Your little sample goes in what we call a cuvette. It's like a test tube, but it has a specific line that you line up. There's a line on the machine as well. You push that down there, and then it reads it. Currently, I am at wavelength 526, right? I can use this knob to change my wavelength. Somebody remember a wavelength in blue? Is it 800? I thought it was 670 something. So if we take a look, I'm gonna go up to 680 for my wavelength. Now notice there's nothing in there, but I have a negative 4.6 transmittance. So what I need to do is adjust that. There's a 0 and there's a 100. I need to turn the 0 knob so that it's at 0 because there's nothing in there. Did I go the wrong way? What's 680? Man, so this is red. So let's do this one first. I went the wrong way in my head. So notice I'm really close. Now you guys are used to a lot of things that are digital. This is totally analog. So keep that in mind. If it's like that, then you're close enough. Now what I have here is called a blank. And a blank basically is just pure distilled water. I want to make sure that my blank is wiped down so there's no fingerprints. So notice the only place I'm holding this is above the part because that's not going to be exposed to the light. I also want to see if there's any bubbles or anything. And if there are, I want to try to get rid of them. One way I'm going to try to get rid of it is to just blow it out. blow it off the side. And the higher the bubbles are, if there are bubbles there, the less likely they are to be in the beam because you're only looking at about the bottom part of that. So let's put the blank in there. So I've already got it zeroed. Now I put the blank in there. So basically I want to take out the medium. So the medium in this case is water. So I want to change this to 100% transmittance. Basically, I want to tell it that without, if the water's there alone, there's no absorbance whatsoever. So I'm calibrating the machine. Notice this time I'm using the 100. Oh no, that's not right. Huh. Wait a second. Yeah, you know what it is we're probably too high up on the wavelength. Let's try another one. Let's go down. What'd you say? 400 was blue? That's what I wanted anyway. Let's start with blue. I think I was just too high up on there. You can only go for certain ranges. So again, we want is my brain thinking correctly? We want 0 here. Am I thinking correctly? Let's see, with light. Come on, 0. That's the thing about analog is you could press a button on something digital and it'd be like, okay, I get you. And watch this, I'm gonna touch it and I'm gonna go over. Hey, dang it. Again, if it's blinking like that, you could go with that because you can see how testy it is. How much fun is this though, right? Blanking. So we want that to be at 100. So you can see some people are like, well, I'm turning it and it's not changing. That's the beauty of an analog thing. You can keep turning it. Never force these though. Never ever force these. So I'm going to get this down to transmittance of 100. So 0 without anything in there, 100 with just distilled water. Right?
Wait, but wouldn't that be 1,000? I'm confused.
No, you can't see the decimal place probably.
Oh, okay.
Yeah, sorry about that. Yeah. 100. So now that we have it at 0 with nothing in there, 100 with the distilled water, now I can go with my solution. Remember what's the solvent of my solution?
Water.
Yeah, water, right? Distilled water. So basically I've accounted for the machine not seeing the water. It's only going to see the particles in there. Now with this, I don't want the amount transmitted. I want the amount absorbed. So see, we're on transmittance there. If I hit mode, now I'm on absorbance. So that's 0.506. Remember the numbers from, well, you can look down at your sheet or whatever. Remember the numbers from your, from that graph we just looked at? So for 0.201 molar, that is 0.504 absorbance, right? So we have the molarity because that's the solution at its strongest content, and we have the absorbance. So then what you're going to do is you're actually going to do this very well, and you're going to make dilutions. I don't have time for that, so I'm not going to do as well, but I'm going to try to dilute it by half. I think you guys do 4 different dilutions in the laboratory. Now, the biggest thing with this is you have to use the same cuvette every time, because what if there's an imperfection on this cuvette? Then it will be messed up, right? Then it will not have the same look as it would for my other ones. So again, we don't have anything in there, so this needs to say what? 0? Oh, I'm sorry, I'm on absorbance. I need to be on transmittance. At transmittance, we need to be at 0. We need to do every single part of this again. So we have that at 0. And sometimes, like, I mean, if I hadn't messed with it, we might have been okay. Now the blank. See, we didn't touch the 100 one. You're not paying attention. So we are actually very close to good on the 100 one. Come on now. What is that? Are you bored? You still feeling daylight savings? Come on now. Yay, analog. All right. So then we would take this new solution that had the dilution made, make sure we're lined up. And again, we don't want transmittance for the solution. We want absorbance. So we went from, somebody help me, 0.500 something, 0.506 to 0.318. Now, remember, I did not perfectly do a half dilution, but you can see what's happening here. We're going to get a nice straight line. And without anything in there, again, the point is 0, 0. That means that then once I make that line, if I have an unknown solution that I don't know, I could just sit there and take and put that in there and be like, oh, well, the absorbance is this. I can go to that line then and find the concentration. So that means I could sit there and test all of your guys' solutions to check to see how close to 0.200 it is if I had that line, right? By just looking at the absorbance. Pretty cool. And one last thing, again, somebody write this down. Will you write this down? This is 0.314 absorbance at 450 nanometers. 0.314 absorbance at 450 nanometers. So I'm going to change the wavelength. We said we could not go to 660 or whatnot. I'm going to change the wavelength to, what was I at before? 4 something, 450? I'm going to change it to 530. We still have 0 transmittance. I'm going to pop in this guy right here. We see that we have 144, so we need to go down to 100 on that. This is again in transmittance. The cool thing is they can use this to do a lot of different things. Like, for example, find the dissolved oxygen in a solution. Find other things, poisons and stuff like that. Again, I'll make sure that I wipe this completely. And we are now at 530 nanometers. So we go to absorbance. And before what we were at 0.3014, you can see that this is 0.534 here. So do you think that 530 would be better to measure absorbance or worse than 350 or whatever we did?
Better.
Yeah, this is higher, right? This is higher. So that will give us a better curve. So what you want to do is you want to find the best wavelength. That's what you'll be doing on Thursday, is you will, instead of changing the dilutions of this, you will take your solution and you will change the wavelength by 10 each time.
So we like start at 400.
Yeah, you got it. And the worst part about it is you'll do this a few times and you'll forget that you're on absorbance there, just like I did, because it's been about 2 months since I've used one of these, and you'll forget and you'll be like, oh no, my zero is messed up. And I'll come over and be like, oh, you're on absorbance. So we have that blank there. We went up to 540. We check our total transmittance, which should be 100. It's going to be different because we changed wavelength, but this one should be a little quicker to change. Mirror you, because we should be pretty close versus the first time we tried it. And then we will pull this out and put in our blank. And notice how many of these I'm using each time. It's kind of like a dinner. You should really only need one napkin for dinner. Unless you're slop.
So
These
every
are-
time.
These are
Patent.
different. These are different than the neighbor. These are more like tissue. They're called chem wipes. Every time you've got to wipe it down just in case your fingerprints got on it. And again, we don't want transmittance. We want absorbance. So is 540 better than 530? No, it actually went down, right? So basically when you do this, you're going to make a graph and you're going to get a curve. You want the wavelength that's at the height of that curve. Is it not called a curve still? Is that not a
Wait,
curve?
so I'm confused. When should we change the wavelengths?
This is Thursday's lab. You change the wavelengths between all tests with the same chemical, the 0.2 molar.
Okay.
That's to find the best wavelength. You might have to read through, but I think you'll get it with that explanation a little bit better. The first day you're finding the wavelengths that works the best, and that's Thursday. Cool. We'll check again if you have questions or anything about it tomorrow. We'll run you through a pre-lab, because the key thing is hopefully Thursday when you guys come in, we can just go. So I want you to make sure that you kind of get the most of it before Thursday, because otherwise we won't have the time to get it done by Friday, and then we'll take more time on Tuesday. What's showing right now? Did I delete you guys? Are you there? There you go. Not sharing. All right, cool. So what I would suggest for this evening is you run down through these problems. That's a big, quick review of all the problems possible. But remember, if you need help with definitions, there's this Scrabble thing here. If you need help with maybe relieving yourself of choices, there is this test-like review. And then there is extra molarity problems. Those are the basic molarity. If you're having difficulties with that, that's a place to start. If you're having trouble with what we did on Monday, and that seemed to be a thing, you have all of these different ones here. And again, I will try to get the answers to this complete packet up. I'll try by the end of the day today. I can't promise anything because I'm quite busy. That's why I said like I can't get anything else graded if you're turning in late work. But that's what I got for you. Olivia, if you want to stick around and ask questions about that machine or whatever, by all means, you can. But it might be best if you read through maybe the first page of the lab first. Other than that, have a great day, guys. If you need something, stick around, obviously, and ask. But other than that, I will see you. Bye.
So
What's that?
when we're putting in like the colored solution,
Yeah.
do we start with the lowest wavelengths? Like what did you do, 360 first?
Give me
then
1
go-
second. Let me grab the laboratory
Okay.
and I'll share that with you. So it says you will start with it at, let me zoom in. It says you'll start with it at 400.
Okay.
And then basically you will go down through the steps that I talked about, but they're written out so you can see them better. and then you will increase it by 20, and then you will go through the same steps again. And then you will increase it by 20, and you'll go through the same steps again until basically you reach the point when, what did I start with? I started with 650. Yeah. Yeah, and you can see that you can only go up to 640 from it. So then that's whatever I put it back all the way down. So you'll start at 400, you'll go up to 640. Some of these machines may not even be able to go up to 640.
Okay.
But that's with just your original solution. So all you'll do on the first day is use that cuvette, and then you will need to graph this, and you will be looking for the maximum absorbency, which will be the height of the graph. The
Okay.
curve. And
And I
then on the
don't-
next day, that's when you will come in and make your dilutions. You'll make 5 dilutions, and then you'll use that maximum wavelength and then measure that, all of those at that maximum wavelength. So these 5 dilutions, that will take some time to make, but actually pouring them into the cuvette, that should not take any time at all, right?
Okay.
And then dropping them in. Yep.
So for my highest, what'd you call it?
Wavelength.
Wavelength. Does it matter if it's in order of how much I increased it?
No, actually, if you do a very good graph, you might be able to sit there and get, like, if you see 2 points that are like here and here, you might be able to extrapolate the data of it being higher than that point. You know what I mean? Like if you got 560 and 580, and you notice that they were down here, then 560 and 580, except 570 might be better, right?
Okay.
Cool.
All
I
right.
have
Thank
a
you.
question about like the saturated graph things.
Yeah.
I'm confused why when it's below it's super saturated. Because like whenever I would like, because in class and
So
like sometimes you
here's
would
the
say
thing
it
is
was
you're thinking of the dot. You're thinking of the dot. You need to think of the line. Does that make sense?
I need to think of the line.
Yeah, on a big thing like here, let's think about the dot.
Mm-hmm.
Can you see that okay?
Yeah.
Yeah. So we have A. That's the dot, and here's the line. If we have A grams dissolved, are we saturated or unsaturated or supersaturated?
Super saturated?
No, if we have A grams dissolved, we could still dissolve that many grams
So that means it's unsaturated, right?
unsaturated. If it's on the line, then that means it is
Saturated. And when it's above, it's super saturated.
above the line, it's supersaturated.
So I'm confused on the thing. I got 26 out of 30. And for super, I'm like confused because you said it was super saturated when it was below earlier. So I'm like,
Now take a look. Because now we're not looking at the dot, we're looking at the lines.
yeah.
So C, the line is below the dot.
Mm-hmm.
So that means that C would be supersaturated if it were dissolved at the dot. The other ones are unsaturated.
Oh,
It all
okay. So above would be super saturated,
no,
but
the,
no. Like for
dot,
this,
yes.
I know what you mean, but like I was just reading it wrong because I know like for C, since it's X is above C, it's super saturated, but C looks like it's okay. I think I just read the question like in reverse.
So that's the thing. You're looking at one of two things. There's a way to look at it. Like this picture right here is looking at the dot,
Yeah.
and being set, and the lines are what you're actually asking yourself about. Here, the line is set. Where'd it go? The line is set, and there's a bunch of dots, right? So I mean, that's the thing. Yeah, you have to really. That's what I meant whenever I said, put your idea. Actually, put your finger on the dot or something like that. Am I on the line? Because if I'm on the line, I'm saturated. If I'm over the line, I'm super saturated. If I'm below the line, I'm unsaturated.
Okay, I think I was just I got the concept. I was just confused
I
about
think
the
you're
word.
reading it backwards or flipped.
Yeah.
Wait, so
thank you.
Mr. Jackson, will you give an example for that specific graph? Because no, I'm confused.
What do you mean?
Like an example question for that graph.
For this graph?
Yeah.
Yeah. Which of the following A, B, C, or D is saturated? I don't know. That's pretty ugly. Yeah, that's probably the best right there.
Okay, is there a dot on the line?
There is. It's that guy right there. It's a B.
Oh, so B would be saturated.
And which 2 points would be unsaturated or unsaturated?
C and D.
C and D and A. If you no, I'm
Would
sorry.
be
C and D would be supersaturated and A would be unsaturated. If
But
you
C and
had
D are-
this amount, they're above the line, right? So at what 12 degrees, that dot right there says saturated. These guys are above. We're saying we have 30 grams. C is 30 grams dissolved per 100 milliliters. And on the line here, it is about 17 grams per 100 milliliter. So C has 30 grams per 100 milliliter. And saturation point is 17, right? C has 30. So we have more in C. 30 grams is more than 17 grams. So that's supersaturated, and this is unsaturated.
Okay. Will there be stuff like that on the test, like with the two different graphs? Like when we
That's the thing. You get one of the graphs and you know, that's how we make multiple versions of the test, right? The problem with it is that you have to look at the dot. So if we're looking at the dot, is A saturated, unsaturated, or supersaturated?
unsaturated.
Unsaturated. You're better at this one, aren't you? With the
Yeah.
one, yeah, with the versus the one line. Yeah, I get it.
Yeah.
Cool. You could probably look up solubility curves and some type of quick video on it may help you on both types of those questions.
Okay.
Or review the sheet that you did. Any others?